Hey everybody, this is Larry. This is the 24th of June on the June Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Out of boundary paths. So I usually solve these live. So if you what was I gonna say? Oh yeah. So if it's a little bit slow, take fast forward, watch it on 2x, whatever you need to do. And let's get started on today's problem. It's Thursday. Happy Thursday, by the way. Hopefully everyone's just chilling and doing all right. Okay. So you can make max moves to the board. You can, given the 5 integers, return number of paths to move the board out of the grid. Okay. Since the answer can be very large, return it 10 to the 9 plus 7. Okay. One time. So, okay. 1, 2. Okay, so what I was double checking now is just to make sure that if I go up and down, it's 2 different ones, and then so forth. There are a couple of ways we can think about this for sure. I can maybe do some math around. You can maybe do some math around. Let's get some constraints real quick. But you could maybe do some math about number of ways you can stay within the bounds and then subtract that from the total number of possibilities, and then that would get you the way as well, because every move there are 4 choices, so then you get essentially 4 to the max move number of total moves. So if you subtract from that the number of ways to stay inside the grid, that would be good. And another way is, of course, just count the number of ways to go outside, which is straightforward as well. Well, for some definition of straightforward, I don't think this is that easy, or that hard, but that's not that straightforward, I suppose. But the thing that to note about this is going to be dynamic programming. So, and I'll start the dynamic programming solution first. There's actually a cool matrix multiplication solution as well, but I'm probably not going to get that deep into it. I will probably talk about it a little bit later on, but only to give you hints to as an upsell. But if you do want to solve it that way, feel free to kind of go skip ahead, or maybe someone else made a video about that. But that is also definitely math that is beyond necessary, as far as I would imagine. Yeah, I think that's probably okay. So anyway, let's see. So the dynamic programming, the canonical, the straightforward quote unquote way is that, okay, so give me a second. I am actually gonna bring up some visualization, which is why I'm taking time a little bit, and I am doing this live, so it takes a little bit of time. But yeah, so the idea here is that, okay, one move at a time, you could do a DP on it. I wouldn't call it simulation, but let's just say, you do a count, right? For example, let's say n is equal to 0. So at step 0, everything is going to, at the beginning of the time, let's say we wanted to put in here, right? There's only one way to get from the start row start column, and that's here. And then now for the first move, that your number of possibilities are going to be here. Let's use a different color just to kind of mix it up. Here, 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 and here, and now here's going to be 0 because you have to move one step, right? And then the next one is and you could kind of think about it as a breadth first search as well, a little bit, on a extra dimension, which is the number of moves that you do. And then now, of course, the next move you're going to do is just 2. Oh, wait. Whoops. Well, how many ways are there to get back into the middle? Let me choose to change the color again. So the way that we go to 0 is because there's 4 ways to go, from the original spot, you can go up, down, left, right. So now there's only one way to go left, one way to go up, one way to go right, and one way to go down, and 0 way to stay in the same place, right? And then now let's go another move. What's going to happen? Well, let's say we're here. We can do 1, 2, 3, 4 different moves, and then this goes out of bounds. Oh no. So then this is, well, this is going to say, let's just say this is 2 because there are 2 ways to get here. There are 2 ways to get here. Now this is a 0 because there's no, after 2 moves, you know, you have to, but there are 4 ways to get here. So you have some sort of 2, something like that, right? Roughly speaking. And then of course, as we talked about, and this goes outside as well, and of course this extends further. So this is 1 and this is 1, right? So that's basically the idea here. And you can, as I mentioned before, you can do it 2 ways. One, you could count the total number of moves minus that by the number of moves that are for each cell after max moves, or you can do something that I think I'm gonna do as a fun hack. Maybe. No, maybe not. Maybe that's fine. I was gonna actually. Yeah, I mean, I think you can just count the number of ways it goes outside, and then just count that total way. Because once you leave the box, you can go back in, right? So that's kind of the idea. So you actually lose some possible moves if you think about it that way. I think either way is fine, to be honest. It's just, you know, it's just two same side of the same coin. I know that's not the same, but this is more or less the same. So that's what I'm saying. Okay, so now let's get to implementation. So one thing about this dynamic programming is that for me anyway, I'm going to do it bottoms up. It's not. It has some kind of tie into what I said earlier with respect to kind of like a breadth first search, in that if you know the order you want to visit the array or the states, that is basically how you do bottoms up, is that you kind of go calculate the result of the state in an order that you know how, like in the order that enables you to already know how to calculate that state. And in here it only makes sense to go from go from 0 move to move 1 to move 2, move 3, ... right? And then the key thing to know there is that you only need the previous move. So you can do a space optimization there. So I think today I am feeling like I'm in the mood to do the space optimization. So I'm going to teach that here. So let's, with all this background set, let's finally actually get started. I'm going to do not naive, but the bottoms up dynamic programming, and then I'll go over how I would change it to space optimized. Well, we'll see. Okay, so let's just say count is equal to 3-dimensional things is always a little bit tricky. So we want. Okay, let's just do moves on it. Outside is it moves +1? Yeah, I think so. Okay. Which one is M and which one is N? M by N. So M is rows. So let's actually. I don't like the M and N thing. So I like to just, because it's more straightforward. So yeah. So this is rows. Oh, I can't do it this way though. But is this right? No, it is not. 3-dimensional matrices in Python always confuses me. Okay. So basically we want this, and then we want this, and then we want this, right? let me just run it real quick just to see. And you have to do it this funky way because otherwise you repeat array pointers to the same memory address, and it's something that you'll have to get bitten by once to know. But anyway, so yeah, so now we can just do, let's just have an outside count is equal to 0, and then now let's simulate it, a sort of simulation. We start our base case, which is move 0, start row, start column is equal to 1, because there's only one way to start. Let me just double check whether this is 0 index or at most max moves. Okay. Does that change anything? No, I think that should be okay. And then now, oh yeah, mod song. I remember reading this, but because I was doing my explanation, I forgot. So I have to do mod because otherwise I will forget. And this won't compile, but that's intentional because it'll remind me to run anyway. I say compile in Python. I just mean there'll be a runtime error. I forget what the error is, but it'll just give you an error, right? Like it'll be like, this code is not good. Yeah, runtime error. Anyway, that's intentional. So now we can just do row by row for max, for move in range from move 1 to the max move inclusive. So now we go for X in range of rows, for Y in range of columns. So now for each cell, we go, I guess there are two ways to do it. Actually, let's do it the other way. So basically we start, we populate. So there's a push or pull DP, people say it nowadays. I don't really like the term, but you can go both directions. I don't think it really matters that much, but I think this one is a little bit more clear. So then now counts of, well, let's do directions is the 4 directions. So let's do, well, I don't know, something like up, down, left, right, but it depends on your sense of direction. I cannot type this today. Okay, so now for dx, dy in directions, the next x and the next y is equal to x plus dx, y plus dy, and then, so let's just, and usually I don't need the variables, but I just want to illustrate a little bit. So current moves is equal to counts of move xy, and this means the number of moves to get to, the number of ways, not moves, ways to get to xy on exactly moves. Okay, so now now we did what we said earlier, right? Now here we can go up, down, left, right for the next move. So we have 2 checks, and yeah, I think that's pretty much it. So if nx is within bounds, then count of move plus 1 nx and y, so the new position is equal to, oh sorry, we added to the current moves, else we got outside, so we do outside count current moves, right? And that's pretty much it. There are some, I mean, I think technically you could even just do this and that'll be okay. Let's give it a spin. But there are a couple of things we want to do, so, you know, to make it clearer, or was it 50, 50, 50, 4, 5 should be good. There are a couple of things we want to do for mod as well, now that we have a mod, so that it runs a little bit better, but it should be okay. Or it's okay, but we'll make it slightly faster as well in 2 directions. So there are 2 things here, right? One is that, you know, this is dynamic programming, and the key thing is keeping track of mods. So let's actually do that here. So every time we change this, we change it by mod. this should not change the answer, at least the answers that we have, at least in Python. Because, yeah, this looks good, though the time is actually a little bit slower because we're actually doing a lot of mods. You can do some optimizations like checking if current moves is greater than 0, though. I guess that, yeah, why not? It doesn't really matter that much. Or the big O notation is the same, but I guess in actual performance will be a little bit faster. Let's see how much faster. I'm just curious now. So yeah, so a little bit faster, but it's not necessary. It doesn't matter either way, because obviously otherwise you're just adding by 0, but then you also mod, which is why it's a little bit slower, or a lot slower depending on how you would find it. Anyway, because half of the moves are not possible at any given time, in the sense that if you have a cell, you could think about it like a checker or a chessboard or something, where you're always going from white to black or black to white. So therefore, half the cells are always going to be 0. So you can say that this optimization actually makes it twice as fast. And these are just random things I'm thinking about on top of my head. So okay, so let's go over the time complexity. So this is O of 4, which is O of 1. This is clearly moves times rows times columns. So this is O of, say, M for moves times row times column. I know this is not the notation that they use, but that's fine. So yeah, so that's the time and space, because we also do that here. So one thing to note is, of course, that move plus 1, if you look at the previous, I think I did this in a previous video, but the idea is that, and let's pretend this is a one-dimensional row for now, so that we can have an illustration. Pretend that it is this case, whereas 1 by x. This is just for visualization. So then let's say you have a lot of zeros. And then the next move that you can do, you go, this is just me simulating it, right? And then the next one after that, we look at this, we see this one, we can go here, and this becomes a 0, this becomes 2, because this has 2 contribution, if you want to call it that, and so forth, right? And that's basically the idea here, though this looks actually, I guess the one-dimensional one is just Pascal's triangle variation. But in any case, right, the key thing to note is that, let's say this is one-dimensional, and the me going down is just the moves dimension or time dimension or whatever you want to think about it. But notice that when we change this move variable, when we're processing this row, we only look at this row, right? We never look at the previous 2 rows or whatever before that. So that means that we can actually throw it away. And that's basically the idea behind the space optimization of dynamic programming, when you need to fit in the space. So here, you can even think about it straight up as this. Instead of just max move plus 1, you can do it as max move of 2. And then we look at only the 2 numbers. And here, and I'm doing this in a different way. There are definitely different ways of doing the same thing. So I, try to import what you feel is more intuitive, what makes sense to you, and what to understand it. And of course, this code will give you an out of bounds error, because hey, your move is out of bounds, blah blah blah, right? So yeah. So then the key thing to do is that now, knowing that you only need the last 2, then this is the current moves, I guess. The way that I sometimes do it is just I mod it by 2, because now you have a binary thing, right? And that's most of the way there. It's not quite there yet, because we're doing adding. So because we're using the same memory, we have to reset the memory. So basically, we just have to add another loop, and you can maybe use the notation of, you could maybe do something like this is equal to, this times whatever. But of course, this allocates new memory. So this is why I need this for loop thing, even though it is a little bit more yucky in time. So something like that to reset the time, right? And of course, there are a couple of things that you can do here. for time optimization as well. Let me double sure that is right. You know, it is pretty fast actually, relatively fast. The thing to note is that you're doing this mod operation a whole lot. So let's just do current move is equal to move mod 2. Next move is equal to move plus 1 mod 2. So then now you can just reference that instead. These are just like minor optimizations, but sometimes it adds up depending on how you do the math. In this case, it's actually only 50 cubes, so it's not that big of a deal. But conceptually, there are also things where you can just use two matrices and then swap them back and forth, but you still have to remember to clear them. And, you know, it's the same idea. This one actually ended up being a little bit slower, but I think that's just a fluctuation on Leetcode's time. So yeah, when this is fast enough, it's not that big of a deal. So now let's give it a submit before I rant a little bit longer, just in case I have a wrong answer, because that would be embarrassing. Okay, because I spent 20 minutes talking about it, and then yeah. So this is good, accepted. So what's the complexity here, right? Now again, the time hasn't changed, but the space, as you can see, is that we have 2 times R times C, which is of course just O of R times C. So this is how you do the space optimization in case you want to learn it. I mean, you can see that I did it very quickly. Just minimal. I even have a whole video about doing this, maybe with 80% of the visualization. Let me know what you think about it. But yeah. So I did give a little bit of a spoiler in the beginning of this video about the matrix multiplication. So the key thing about matrix multiplication is that noticing that we can think about, and this is a little bit expensive for some small MNs and notably max moves, because basically you're trying to have M times N states, and for that you have transitions between those states, and then from that you can calculate a matrix multiplication type thing based on the max move. Because the key thing to note with matrix powering, maybe that's a better word, matrix exponentiation. Is that the word? But the basic idea is that now you have a transitional matrix that you want to run max move of time, which is, if you remember your linear algebra, then it just becomes, essentially with a transitional matrix, you have A times, which one is the matrix? I always forget. But you have, say some X times T for one move, and then to get the second move, you times it by T again, and then each matrix multiplication will give you one move transition as you set up that matrix for a transitional matrix. But key thing to note that it becomes roughly, and I don't think this is standard notation. I forget what the notation is, but you get X times T to the N times, where N is the number of moves, and then. But noting that T to the N can be calculated in log N times due to matrix exponent, repeat powering or whatever it's called. So from that, you can be able to do it quicker depending on the constraints of the problem. For this one, you have to do the math to see if it makes sense, but it is always, I think maybe 50 squares is a little bit too big, to be honest. It comes up in other places, but because for example, if this was 1D, 1 by N, 1 by 50, and you have a million moves, that may be a candidate for matrix multiplication, because the number of states is only 50. Anyway, I'm not going to bore you too much, but that's basically the idea. And if you want to read more about it, just, just Google matrix multiplication, maybe a matrix exponentiation, and maybe transitional graphs or something like that with matrix representation. That's basically all I have here. Let me go show the solution while I'm talking. Let's see if there's any interesting hints. There are too many paths, of course. Use some space. Dynamic programming. Okay. From the corner cell, can go up 2 ways. Yeah, okay. I don't know. Is that even that interesting of a hint? I don't know. You tell me. Anyway, this is mostly my code. And that's all I have. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. Hope y'all have a good rest of the week. Happy Thursday, happy. I don't know. Have a good rest of the week. I'll see you later. Stay cool, stay good, to good mental health, and I'll see you later. Bye bye.